Hello, everybody. My name is Dovydas. I'm the president of the Lithuania's AI Association. Today, I'd like to welcome everybody to this really amazing presentation. We'll have our friends from Accenture who are going to present, who are going to show us some tips and tricks how to do image segmentation for computer vision modeling, etc. So really interested in their presentation. And if you have any questions, I encourage or comments, I encourage you to be very active on YouTube. Just to post your questions there, and we'll be able to answer the questions like after their presentations. So let's give a quick welcome to Jelena, who is going to who is a data science and machine learning team lead, and who is going to give her intro and to her presentation. So welcome, Jelena.
Thank you very much. I'm glad to participate in this meeting, and welcome everyone who decided to spend this time together with us and to speak about conversation AI and some tips and tricks related with image segmentation. And thank you for opportunity to join to this meetup. Thank you for meetup organizers for this great opportunity. Maybe first of all, I want to introduce our speaker. Our case speaker is Viktors Roze, and he is our computer vision senior developer and represent our amazing team, computer vision team, which has great experience in this area. We have delivered quite a lot of serious computer vision projects in this area, and our team has participated in many hackathons and took their first places. And we have scientific activities in this area, and we always try to deliver innovations for our clients. Viktor is a bright representative of our team, and he will share today with you some tips and tricks from his professional experience, and I very hope that it will be useful and interesting for you. Yes, I lead data science at machine learning group, and also I'm working as a data scientist at Accenture. Unfortunately, Khodor, our data domain lead, will not be able to participate here as presenter, but he will together with us. And if you have any questions, you can try to ask us about some information about our company and our work. I want to share with you some information about us, about Accenture, Baltic Advanced Technology Center is the largest center in Europe. We have exceeded more than 2,000 talents, and we continue to grow. We deliver our services for more than about 280 clients in 28 countries from Europe to America. Our center was opened in 2002 in Latvia, and maybe you know that we have opened our center also, our office also in Vilnius in last year, and we'll be very glad if some of you will decide to join to us as well, because we continue to grow and we have quite serious ambitions to grow in this area and to grow, of course, in the area of artificial intelligence as well. Some information about our group. I and Viktor represent our data and AI specialty track. It is largest center of excellence in Europe. Our experience is more than 7 years, and current number of talents is more than 200 at the moment. We deliver our services in different areas, and maybe we can group or separate our activities into domains. One domain is related with artificial intelligence, and another one is so-called data domain. Guys who work on artificial intelligence deliver services in the field of business process automation using RPI and AI services and conversational AI development. Under data domain, we have several groups. Of course, we have our group, machine learning and data science. Also, we have data engineering group and augmented insight as well. If to speak about machine learning and data science, we have great specialists who are capable to work in the area of predictive and prescriptive analytics, advanced analytics, deep learning, natural language processing, and of course, computer vision. And as we speak today about computer vision mostly, then I decided to show you our portfolio, what kind of experience do we have in this area. We're really have huge experience in quality inspection, event behavior analysis, anomaly detection, digital twin, and of course end-to-end development. Maybe I will not spend more time for detailed explanation about our experience in this area, because I know that Victor has prepared a few slides about our projects. He will show with you some examples of our projects in this area. Maybe last one, what I would like to tell you today, I want to share information that we plan to have data science and machine learning bootcamp this summer. And everyone who would like to participate in this absolutely free training for 2 weeks can join to this bootcamp. Registration is open, and you can visit our portal, bootcamp.com, and apply for this training. Some of you who participated in this bootcamp can apply for a fully paid internship if you will be interested in it, and you will get opportunity to be hired after it to Accenture. We will be very glad to have new colleagues in our team to work under AI solution development. And now, probably I would like to give the floor to Victor, and he will completely occupy your attention to share his experience in computer vision. Thank you for your attention.
Thank you, Jelena. I hope you can hear me well. Maybe I will now share the screen for a moment. Let's go. Do you see it? Is it visible? Should be. Share the screen. There we go. Entire screen. Boom. And let's go. Is it visible? All good?
Sorry, Victor. It's not visible at this moment. Could you try to add your? I think we are good now. Oh, please come back to where you were just a second ago.
Yeah, it might take a moment. So whenever it's visible.
Just let's wait for a second. It takes some time for apparently for the screen to register in the app, and then I can add it to the stream. Have you tried the same thing that you have just done a few seconds ago? I'm still not
sure. There's a bit of a lag, I think.
Okay, perfect now.
No, perfect. We are good. Okay, so computer vision. Actually, we have a lot of experience in Accenture in computer vision, and especially that's one of my main interests, together with AI, and I have moved into this direction, and that's why I was also interested in Accenture, because it's quite strong here. And actually, we had a lot of experience with computer vision in a special division in Accenture called Liquid Studio, which is driven by innovation. Right. So I would like to share some maybe genres of computer vision that we have looked into over the years, and different things that we can do with computer vision. not just the individual use cases. So the main things we have touched so far are things like pose recognition, where we could recognize different body parts, facial expressions, and use those in interesting projects. Then there is our today's main topic, which is segmentation, where we look into the parts of the picture that could belong to a certain class. And then there is very popular OCR use cases, where we detect different characters, handwritten text, and try to make sense of it. And then there are, of course, the classical object detection and classification use cases that are very strong in our portfolio as well. And then there are a bit more challenging kind of a computer vision genre, which is the anomaly detection. That is also quite necessary in our latest endeavors into factory production control, where we are looking into the quality of the products developed. So maybe we can take a look into pose recognition, which is quite interesting because it works very well with demos. We have this very nice use case where we created a fitness advisor that basically could recognize your full body movements and give you feedback on different fitness exercises that you are doing. So it could say whether you are performing some exercises correctly or not, or give some slight feedback on how to enhance your performance even. Yeah, and then you can see two examples here. One is bike and one is leg stands. And then there is a very interesting examples with sign language, where we focus on the gestures, specifically with hands. We are basically detecting a point cloud in the image and try to connect them to understand what kind of shapes your hands and mouth is making. And therefore, we can translate that into letters and words that we can then show the user, for example. And then there is even more complicated use case with that, where we actually created a live 3D rendered avatar using Blender that used a predefined dictionary of words that are combined then together to translate audio and visuals into sign language. Yes, and that was also very challenging use case. Yes, well, this from technical perspective is interesting because we are getting a point cloud from the image. But then there are other interesting things. For example, we could get a mask from an image using segmentation. And segmentation use cases usually associate with photos of real-world objects like humans, like self-driving cars, where you could recognize different parts on the street in live examples. Here on the right, you can see a great example of pill recognition use case we developed specifically to understand what kind of pills are you buying, and maybe you could buy them yourself. And to validate that you have bought the correct ones, we should take a photo from the bottom of the bottle and check whether the count is correct, the weight, and the type of a pill is correct. And here as well, we used segmentation to detect not just the pills themselves, but also their engravings, text on them, and different obstacles that can be on the bottle. So we could judge which pills are better, which are worse. And that was definitely like an interesting use case. But you can actually use segmentation on synthetic examples, on a little bit more data looking kind of things, like documents, for example, where one of our innovations was to detect different parts in tables to understand how to turn unstructured data in documents like the tables into structured parts. And some of those are so complicated and abstract, like, for example, the headers of the tables, that we actually need to use, it was actually more straightforward to use segmentation to understand different parts of the table rather than some algorithms and semantics. That was actually a lot easier and actually produced very helpful results where different clients could automate their searching process through documents. And actually, you could use that also for web pages, HTML documents, or even code itself, images of code. So segmentation and image processing is useful not in just photos, but also in different other data. And we can use data from different other domains. That's actually a key message here. And then, of course, OCR is also very important in different projects where we have used not just already ready solutions like Tesseract to turn different symbols into text and then try to get some meaning out of it, but also we have experience with our own pre-trained models like custom Keras models, where we want to find specific characters or a set of text that is already predefined and easier to detect, and how to, let's say, translate different forms into, again, structured information that afterwards could be parsed and processed, and we could automate some processes, like reports of scanned documents, for example. That's a popular solution. And then there are a plethora of projects and use cases that use classical object detection and classification, like, for example, smart parking, where you could mark different parking spots, and these spots get cut out and then recognized as free or taken, or there are different objects in the wild that we can detect. For example, a very interesting innovation project we had was actually a robot that was trained to collect apples in the real world. So it had to recognize in all kinds of situations apples, be able to come closer to it and pick it up. And actually, we also trained it in a virtual environment where it was trained using reinforcement learning. And then for classification, maybe interesting example was a fluid classification, where we looked simply at a piece of complicated color, where you could see different colors mixed together, but we should make some predictions what type of fluid it is. And then, of course, in the quality control, detection is also very important, and sometimes even quite complicated, because you might need to detect the count of different screws or little parts and their exact configuration between them. And sometimes the objects are moving in space, so even that could be quite a difficult challenge. So we also had some interesting experience with anomaly detection. This topic was also looked at in the recent hackathon, where we got a very good place as well, with different experiments in anomaly detection. And here again, we have taken examples of our famous pill detection to detect the anomaly pill in the bottle. And we have tried ANO guns, patch distributed modeling approaches that work with mixed results, as it's very hard to find anomalies in images, but still good enough to make a prediction, right? And for anomaly detection, the main idea is to understand the content of an image, by compression and then decompression, at least with anomaly GAN, where you could compare the generated with the compressed images to see whether there are large differences, and the larger is the difference, the higher is the anomaly. Yeah, and then you have to create different solutions, maybe algorithms to get rid of noise, because quite often if you apply anomaly detection, there always, in results, will be some anomalies. You just need to find the right thresholds to say that it's big enough, so to speak. Yes. And then maybe if we are talking about segmentation, it would be good to give some basic introduction regarding what segmentation in images is, and what kind of models we are using most often. So for segmentation, there are two quite popular models that we are using. One of them is developed by Facebook AI Research Center, that is called the Mask RCNN. That's the derivative of Fast RCNN, which is quite successful, works quite reliably, and we have used on many different projects. It can be quite a heavy model sometimes, but you can get really good segmentations with models like those. And then there is UNet, that is a bit lighter and was developed by University of Freiburg in Germany, specifically for some medical research. But it's also, if you need something faster, maybe lightweight, this is also a great solution. And if we submit, let's say, an image to a segmentation model, the output is actually a very large matrix, or several of these matrices, with ones and zeros, usually. And these ones and zeros mark the different pixels, whether they belong to this class or they don't belong to the class. And they are essentially a mask that masks parts of the image, pixels, and they're belonging to this class. So let's say if I would have 7 classes, that I would have 7 of these matrices, and maybe most of them are empty, but then one is full with the mask for this specific class. Yes. And then we can move to the interesting part, maybe a bit practical and technical, which is the actual tips and tricks on segmentation that we have acquired over the years. So one of the first steps for your model training and development probably will be your dataset gathering and labeling. And although it seems quite simple, there is a lot of innovation in this field, because segmentation labeling is quite intensive in work that you need to put in. It's not the same as drawing bounding boxes on image. You have to really mark the edges of a sometimes very complicated object on a large image. So there are 2 main ways how to do it. In the supervised way, you could basically add another image on top of it that would have pixels where every color would represent a class. And that's, of course, is quite time consuming. So we more often use a method called polygon labeling, where we actually draw on top of image polygons, a kind of annotation file we create that annotates the image with X and Y coordinates. It creates a quite complicated shape, which is the boundary of this image, and then we save it as a separate file. And then the most interesting part is, what if we have a lot of data, but we don't have the time or the willingness to maybe label it ourselves? We would like to give just a hint to the AI. So there are some developments in this weekly supervised learning, where we just, let's say, give names to images, like titles, or maybe some points onto it. So in this research, there is a very good comparisons. For example, if you would like to label this image with the scenery, by labeling every pixel, that would take like 1.5 hours for one image. But if you would, let's say, just add the name of the classes in the name of the file and let the neural network itself to distinguish which features were there, where they weren't, where are the boundaries, that could help you to achieve the results a lot quicker on large data set. But the issue is that these weakly supervised learning methods are quite noisy, actually. You see quite a lot of mistakes with that. And the minimal necessary information that we actually could add by research, it's found that it's enough to add these extreme points on object, let's say 4 points, and that would be enough to actually segment the object itself. And you can go even a step further and train separate models just for labeling, where you could, let's say, label a few images, train a model that receives not just the boundary of this labeled image, but also T-points, and learns to generate these masks just with a few dots that could actually reach the high quality of labeling the full image with polygons. But instead of drawing, let's say, 20 or 40 points, you just can put 4 points, as you can see in this example, where we put extreme points on each our interested object, and then it segments itself quite well. And actually, we use such a tool. It's called Dexter, Deep Extreme Cut tool, that maybe as my only demo today, I would like to show you very quickly on these images. I hope nothing will explode, and it will be visible right now as a demo. So I have opened with this program, with this model in PyTorch, my image with pills, and I am just labeling 4 extreme cuts, 4 extreme points. And right now, it should, oh, I actually missed 1 point. Let me try again. You can work also with less points. Whoops. But yeah, you get the idea. You can actually pre-train this model that would help with labeling. Yeah, this is the perfect variant. And this time I pressed the button a little bit too early. But yeah, it's very beautiful. And you can remove those if you don't want. But it's all done with the assistance of my extreme points, and because I have previously trained a model for this. Okay, and that was my little demo. Thank you. And now we can move to the next stage, where maybe we would like to create even bigger data set by a specific trick, which is artificial data set generation, where let's say you would like to label just a few images, but generate the rest of the data by augmenting existing annotations. Or even you could go a step further and render them out in 3D with CGI models, which is actually a very interesting topic. And this kind of approach we did use to test our pill detection software, because it had to work on thousands of classes and it had to work reliably. So we had to figure out a way how to create a huge controlled data set where we could make different experiments on it and also test our models. So right now, all of these images that you see are actually generated with our synthetic data set creation software. So what we did in this example, we took from an image library from dataset that is publicly available, thousands of pills, and we labeled just one of them and added to our dataset so it could read the polygons. Right now you can see the X and Y coordinates for this polygon, and then ran a code that basically augmented them in the boundaries of this bottle and added another layer of the image, which is with transparency. So you could see also the obstacles on top of the pills and generated a very large data set that then was tested on different methods that we used for classification, like deep metric learning versus, let's say, we also used regular classification or regular object detection and see which one would perform best. So these are the results already when we ran through our model on the synthetic data set, and it works quite well. When you can see the pills that are segmented and also these obstacles that could lower the quality of individual pill. So we could actually order all of the pills by their quality. So the best pills would be those pills who have the most engravings here, the most significant features. And those would be then sent with higher priority to a deep metric learning model that would actually compare them and their similarities to other examples of pills and see which pills are more similar to the highest priority one. And then if the results are not so meaningful for the highest result, maybe we would take a look also to the second pill and the third, and altogether, if we concatenate the results, we get a high confidence that our result is correct. Yes, and then the next step that we took was actually to use 3D models and render the pills in a 3D model of a bottle of pills, because this gave a higher realism when it comes to lighting, and also they could stack up these pills in a 3D space. But here the issue is that it's hard to then project the masks, the label in 3D down. It's a lot harder. The mathematics is a bit more tricky. Yes, but this actually method of using 3D models in quality control, especially in different factories, is a very good approach to, let's say, detect expensive defects. Because as you can imagine, if a factory is making defects themselves, it's not so cost effective, and they often happen very rarely, and it's a lot better to take maybe one example and try to create multiple versions or variants of defect in 3D and render that out. And that's the way how you could get a lot better model and see how it reacts with different scenarios there. Yes, but the largest maybe negative is that rendering 3D models and generating data set with 3D takes a very long time. It's very slow, because to get photorealistic images, you actually need to use something called ray tracing, where we are following the path of light rays. And in for example, in Blender models, we had to use cycles rendering, which generates these paths for light through cycles, and actually takes a very long time till we get like good images. Yes, that's why it's a tricky thing. Yes, but then when we have our data set ready, maybe we would want to increase it by another method, of course, that you are maybe already very familiar. It's quite a classical thing, the augmentation with computer vision, like the blurs, your distortions, your rotations, your color shifts, hue, saturation, and things like that. But not always they are good and pretty. Sometimes they are a critical reason for a mistake in model's performance. And we have experienced that actually a lot in production, in quality control, where if you simply remove augmented images, the performance shoots up. That's because if you're not very careful, you can actually destroy very valuable information in your data set with augmentations. So right here, you can see example of image sharpening, where the, I think, main feature of this pill is the engraving of two letters L that gets destroyed in this too aggressive image sharpening. That would be something too strong and actually make our performance weaker. And below you can see a very good example of very slight rotation, which in this example does increase the data set and is valuable. Maybe it's so slight it's hard to see that it's rotated, but if you take a look at this triangle on this edge, you will see that there's a bit more of this triangle on this image. So that is the rotation. But again, even rotation is not always the best thing. And there we actually have some experience with objects that are moving in space. And in each image, we are capturing it in movement. And if we take these images and augment them, let's say with rotation, it could be that they end up in poses that are physically unrealistic. And actually, this augmentation would also lower our performance. So sometimes if the path is the same of this object that moves, it could be better to not augment with these tilts, rotations, and perspective changes, because first of all, such situations will simply not occur, right, in the actual inference when it's going to run. And it's just going to confuse the model too much. It's a lot better to show something that is similar to what will actually happen in the real world. Like, for example, if the lighting in the environment will change. So in this case, the sharpening actually worked quite well. Yes, and therefore you should be very careful with augmentation. And actually, a good trick and tip for augmentation is to use image editing software and automate it to make very gentle and very precise augmentations and changes to images that could help. For example, I do use quite a lot GIMP, which is an alternative to Photoshop. It's a image editing software that you can automate by writing in Python a plugin in a library called Gimfu, and you can then run it with Scriptful and automate the GIMP itself. And there you can not just draw, use different brushes, but create layers and, let's say, add some lighting in the corners, change the background of the image slightly, the colors in a specific place, not overall, and layer it together, let's say, with noise or noisy particles, for example, if I would want to test pill detection on different levels of particles that are accumulated in the bottle. I could just make photos of the dirt of these particles on a glass and then overlay them with the actual bottle and increase or decrease them and make tests like that. And there is also a GIMP CLA tool, command line tool, where you can create different batch processing as well, which is very helpful. Also run these plugins on your set of images. And this is actually my preferred way to augment images that are very valuable. Let's say in production, there are some things that happen very rarely, specifically in quality control. And then maybe I have just a few images that I really need to carefully augment. So in case this rare occasion will happen again, I have a better chances to capture it and make correct prediction. So very good augmentation here would help as well. Yes. Then maybe I would like to talk about how a segmentation model, when it's done, it could not just work by itself solo and create results, but actually work in a chain of different models, which is also actually how often it happens in the different production models, solutions, AI. For example, what often happens is that you could use a object detection model that approximates where is our region of interest, which we would then cut out and then send to segmentation model, which would then do our feature engineering, highlight some very important parts of the image, and then we could use the classification model for the final stage. And here we need to be very careful because we need to train and prepare our, let's say, segmentation model to be the best input for some other model, like the classification model or even deep metric model that was also doing the classification. And then we need to understand what would be the best processing of our mask that we could use for this next model. And then we have also made some experiments on the backgrounds of these masks. If we would need to send the cutouts of our object where the cutout is actually visible, it's like a square image, we actually need to somehow obscure the background and use the mask like that. So we have compared different colors in background and even blur the background, and we have found out that the best color, if we have to use one color, is actually gray. It might be because it's like a middle value, right? In the neural network, it doesn't create such a hard activization around the edges. That could be my guess, mainly because what works even better is actually blurring. Because of these very small differences, I would say that creates even less the activization. So you'd actually focus on the good and important features in the middle of the image, right? And here you can see that the accuracy of our test sets was the best with the blurred background, specifically for these pill images. And then there could be a special procedures that you could do in order to create the best training data set using your segmentation model that could then feed, let's say, your classification model. In this case, we took the original bottle image and we added mirrored images on all sides. So when we would create these cutouts on different angles, you can see it like rotates the square cutout. We would teach the next neural network that the background is really not important. You can see the same pill, but the background is changing all the time. So don't pay attention to it. And always we have the background visible. All right, even if we are close to the edge. If we wouldn't add mirroring, then we would have, let's say, a black spot somewhere. And this has actually worked very well, even if the object is small in this cutout, because the size of an object is also important, and it is its feature. So that is something we have also found out through testing. And then other things that we have implemented in different use cases with masks is margins or algorithms that augment the mask. For example, in this case, we have a pill mask, which is quite rigid. It's not that smooth. And we are often losing this very nice edge of the pill, which is also a feature, and we would like to maintain it. And we are okay to add a little bit more, some pixels to the mask, even if it's outside of the pill. So we have custom algorithms in pure Python that we run for that. For example, this algorithm is what expands this mask by a given amount in pixels. And in this case, the mask itself is a Boolean mask. So instead of ones and zeros, it's true and false. That's why you can see those true and falses here. And it expands in all directions and saves these very important features. And it's also good that it's in pure Python, because then we could add some extra features ourselves. We don't have to rely on, let's say, NumPy, or if it would be compiled somewhere else, let's say, right? Because maybe we would like to smooth out this edge or add something else, some extra rules. Yes, and actually similar approach was used to denoise a mask in our garment change use case, where we created a innovation specifically to try out new clothes. So in this scenario, you can see that a person can stand and we can segment parts of his clothing and then replace with some clothing from a library that is saved. And you could see how this clothing looks on you, so you can give, so you would have some impressions whether it fits you or not. But for that, the mask also needs to be very even, not noisy. On the left, you can see quite noisy masks, actually, with a lot of holes. So this similar algorithm that loops through every single pixel in the mask and checks what is the status with the neighboring pixels was used to fill out the gaps, basically, and make it more smooth, and basically to denoise it. And this works quite well, and we can change your clothing with such a thing. Yeah, very interesting use case. Yes, and then we are going to a little bit different direction, which is how to use segmentation on a data that comes actually from a completely different domain. And this is actually one topic that is close to my heart and that I am interested and will soon also try to implement in quality control, which is audio processing. Sometimes we can gauge the quality, let's say, of some device that is working in real time just by analyzing its sounds. And we could say whether it works properly or not. But working with raw sound information is quite complicated. It's very abstract, right? It's time series data that you need to process many times. And actually, it's a lot easier to convert it into a different domain. And this time it is a spectrogram where you can see frequencies in time, these colorful lines. And the y-axis is frequency. The higher we go, the higher is the pitch. And the brighter is the color, and the louder is the signal. And if we go in time on this axis, on x-axis, it's simply the time. So you can see it's some kind of sound that is fading out. And here you can see more stripes. There you can see less stripes. Actually, here you can see less stripes, here more. And where we see more, they are kind of like phasing. They're going in and out of existence, which is an additional complication. But because these bottom harmonics are really healthy, we could use them afterwards for some classification. And here you can see we are applying a mask. We're detecting these harmonics. And we're taking out this mask, and we could cut out a good, healthy piece of them, and then compare which type of a mask it is. And in sound, there are different types of wave shapes, right? And these two sounds are derivatives of a square wave and a sawtooth wave. A square wave is, let's say, even harmonics, and a sawtooth is more richer. It's even plus odd harmonics. So right now, if we simply count their count and their distance, we could classify that this example is even harmonic example, and the one on the far right is actually even plus odd harmonic example, which is richer, which means that this device is more noisy, it's more richer with tones, basically. So it means it probably is broken, or there is high probability that something is not good with it. And this method, of course, would ignore noise, if there would be noise in the background or other random sounds, because we are specifically looking at the tonal information of the sound. Yes, and this is my most interesting use case, my most interesting future endeavor. And that is pretty much it from the side of segmentation. I hope you liked, and if you have some questions or other things you would like to maybe share, then I am giving the microphone further to you. Thanks.
Thank you very much, Viktors. It was amazing, very interesting. And we actually have one question right now. Jonas is asking, have you tried transformer-based models for segmentation? Is it worth a try in your opinion?
Yes, it's very interesting. We would like to do transformers as well, but we haven't yet had the opportunity. I think my colleague Evrim actually has, but yeah, it's definitely is a thing that you could try. Absolutely.
Right. Not seeing any more immediate questions. Yeah, let's give everybody like a second to do that. By the way, maybe you can talk a little bit. So that's my question. Maybe you can talk a little bit about where this area is moving in the future. What are the like latest current developments? Do you have like your personal, predictions? What's going to happen here? Just curious. What's the future for this area?
Yeah, I think the main blocker for development for the longest time was actually the speed of computers and the hardware, because from mathematical side, from theoretical, everything was ready, and right now we're catching up. So as the price of these devices, not just the GPUs that are famous for enabling AI, but also dedicated devices and capabilities in cloud, now a lot of clients and companies can afford to implement computer vision and deep learning solutions and run inference in different solutions. And that is something that really moves it forward. But of course, custom solutions is what could move it forward. For example, when we are taking images, we're making them in a way that is consumer based, right? In the red, green, blue color spectrum. And we are basically using technology that wasn't made specifically for AI. But where it's now moving is when the light is collected and transformed raw from the sensors in the best way, for example, to make very good predictions on images, together maybe with other data like infrared information as well. That you can see, for example, in self-driving cars, also this advantage where it doesn't matter are we driving in dark or in light, the performance doesn't drop, for example, that much. And the inference is very fast because you have hardware specifically optimized for this information. And it's basically built into the chip. And actually, if I would speak a little bit from the technical side, we have for the longest time waited for AI capabilities to be put into everyday devices. For example, maybe you have heard that the chips that we use for computers had a special instructions called AVX512 that were used for the matrix multiplication that enabled, let's say, real-time face recognitions, for example, on cameras and things like that. And that is actually moving even further, where that's maybe abandoned, but every chip would have in the future a separate accelerator for AI, which means that it would be very accessible, not just in mobile phones that we can see, but also in laptops, in industrial devices, and it would be accessible then, of course. That would be the main, I think, breakthrough, because from theoretical part, there is already a lot of models and ways how we could improve our results. We just need the compute, I think. That's the thing.
All right. Yeah, I actually personally remember ordering, server CPUs that definitely have a AVX512 for the bit faster inference, but back in the day. We have a couple more questions, so I'm gonna move straight to them. So Prasham asks, says, "Hi Victor, thank you for the presentation. Can you share more about the apple picking using robot task? How do you set up virtual environment for that? More specifically, how to reassemble the target, in this case Apple, in the virtual environment?"
Yeah, that was quite interesting thing. Maybe even my colleague Daria is now joining from the other side of the screen, which helped me to. I was actually helping her to develop this use case as well.
All right, let's try to add Daria if we can. Right?
No, of course I can explain, but
Okay.
I'm just giving a shout out actually to Daria. Yeah. But the basic idea is like this: that we would create a virtual environment like a 3D game. In this case, it was gazebo, where we would have these balls, colorful balls, which are the apples, and then using reinforcement learning. At the beginning, the robot is moving randomly in this space, and each time it randomly just picks up the apple, it gets like a positive point. You get a reward, and this reward goes into the loss function of the neural network. Basically, it's like you're getting a treat every time you do something correctly. You're getting a treat, and through this reward system, after millions and millions of iterations, the robot actually learns that it needs to get closer to the apples, because we actually did put a reward if the apple gets larger in the screen, actually, right? So you would have, let's say, like 5 apples on the screen, and if one of them is getting like really larger, you're getting like a plus point, and if you take it, you get a big plus. But if you hit, for example, trees, if you are moving away from apples, you get punished. That's the thing. And of course, we have learned that sometimes it moves quite randomly as well. For some time, it picks apples and then starts to spin around to do something, because maybe it gets too much punished because it's moving away from apples, and it figures out that it's better just to circle around them instead of picking the apples, right? But anyways, yeah, that was our reinforcement project, where we tried to at first train it in virtual environment, and then finally move it to the real world, where it would pick up small apples on the ground. And it was built using actually a vacuum cleaner. We used a vacuum cleaner, a robot that had cameras attached, computers, and this hydraulic arm that could pick up apple in physical world. Yeah, that was interesting.
I understand it was not, like just from a store-bought robot. You customized it quite a bit, right?
Yeah, we hacked it completely. Yeah.
All right, very cool. We have one more question from Jonas. Jonas is asking, so after the image segmentation of the audio signal, use just a simple binary classifier?
Yes, for that case, yes. But you can use many classifiers.
All right. Yeah. I think that's all the questions that we have. Just let's still wait for a second or two. I was quite surprised by this GIMP that I never knew that you could automate these tasks, and that's really powerful, I guess. So very, very interesting. And I guess very, very, I mean, we as like people who are just dabbling with this, we don't have access to like just hardware parts. So this part is, I mean, not as interesting, but like GIMP is so open source, and you can just I can try it out myself. I can see how like if this improves the results, and by how much. So very, very interesting.
Yeah,
At
true.
least for me.
That's the power of open source.
Yeah. By the way, we had like this discussion with like other actually presenters before that increasingly the access to hardware is limiting what type of research you can do. So if you don't have like hundreds of thousands of dollars worth of compute, you cannot really do anything right now with natural language processing, because it's all about billions and almost trillions of parameters. And do you fear that this will happen to I guess to computer vision and segmentation tasks?
I think yes, but in a other way, it's how to tell. It's similar, like with the mining of cryptocurrencies. There's a new generation of hardware, and then everything else is more or less obsolete. Like for example, right now, like the major developments that I have seen is in let's say optics, like optical computing, and for AI specifically, different designs that are not the most classical von Neumann architectures, right, where you have memory and then a place where the instructions are executed, but memory is somewhere in between, and you have different layers of memory. Let's say it just runs through it. Maybe you can debug it. You don't know what's the memory is at this point, right? But the AI-based things works really well. And then if they are available on cloud, maybe for a brief moment, let's say for an hour or so, you can do your research.
Right. Yeah, that's, I guess, in a way, that's a bit concerning, but at the same time, I mean, the progress is nice. I mean, it's still amazing that we are like making things obsolete in such a rapid way. That just proves that the progress is like really rapid as well.
Yes, true. Because actually, the progress of computing was actually getting slower and slower for the past, I don't know, maybe 15 years even. But it's very good that parallel processing was not so much harmed. It was more like this single thread performance. But the performance that we need for AI inference and training actually is more or less intact. We can always see like not in these gains, not in percentages, but in X's, which each new generation of hardware.
Right. We have one more question. I think let's make it the last question. So Lurinas is asking, what are the ways to get into computer vision careers if he's interested in that?
Oh, the best way is to maybe learn some basics, like learn Linux, learn like OpenCV, try to use both TensorFlow and PyTorch, and then apply for some internship or go into some hackathons, maybe meet some new people there, and try to find a place that would accept new joiners. And the main thing is to get real world experience and practice, which is the most important thing. And then it's pretty easy afterwards, I'd say.
Yeah, I guess you're doing the bootcamp. Just a reminder for everybody who was not here. Then Jelena presented that you are doing a bootcamp and later paid internships. So that's really amazing. I mean, for people who would want to get into this field. By the way, are you going to be a mentor there? Are you going to participate in that in any way?
I have before. Maybe I will have an opportunity to do it again. I've done it actually years back. But yeah, that's a good experience. Maybe to give a good start, because if you're teaching some important things straight away, it will help you anyways with better colleagues afterwards. That's
All right.
true.
Yeah, that's amazing. All right. So that was the last questions. Thank you very much. I hope that everybody had a great time and learned a lot of new things. You'll see much, I guess, heavier competition on Kaggle right now, with people knowing all of your tricks. So thank you once more, and see you in our future meetups. Bye bye.
Thank you very much. Until next time.